Hello, everybody, and welcome to your channel Thermal Engineering Concept and Principle. This is Professor Ali Tarat. In this episode and series of different videos, we will talk about an application in the field of thermal engineering, which is the most important application in our heat transfer topic. What are the structural components of shell and tube bundle, heat exchangers, and how do they work? In this series, we will talk about this type of heat exchangers and how can we predict the thermal design of such heat exchangers. Hello, everybody, and welcome again. uh, to present some useful information about the main subject, thermal design of heat exchangers. And in this episode, I will present key parameters that are crucial and important to be considered in the procedures of heat exchanger design. And at the same time, I will present some practical cases to cover what we have um, presented in the previous episodes about this subject. Thank you so much for your support, and let us continue in presenting these topics in heat transfer and energy to support students and junior engineers, and the information could be useful even for the seniors in the field of heat exchangers. Let us go to the main objectives of the present episode. Our objectives in the present video cover temperature correction factor, which we have been mentioned in the previous episodes, that to be used in the thermal design of heat exchangers. Fouling factor, which represent an important factor that affect the heat transfer process in heat exchangers. Then we will present comparison of heat exchangers, heat exchanger patterns, and how can we arrange the inlet and exit ports of both fluids on both sides of tubes and shell. Then practical case studies in the field of heat exchanger design. And finally, we will arrive at the summary. Useful parameters, which are be considered in the thermal design of heat exchangers, we will start with the temperature correction factor. In fact, this factor represents um, the deviation from the ideal conditions for the actual temperature profile in the heat exchanger, and it's account for 1% of that deviation because the main idea of the derivative of LMTD was based on a real counterflow in the heat exchanger that is to be considered in the calculation of LMTD, and this correction factor usually is used to uh, produce a more accurate design of the heat exchanger with optimal efficiency. The prediction of this factor depend on these equations, equation 4 and equation 5, and in fact, this factor can be even presented in cards, as I will explain that in the present uh, slide. We have the small letter t and capital letter T, which represent the temperature in the tube and in the shell side, respectively, and the value of Ft correction factor is equal to 1 for many cases. The double pipe, single pass heat exchanger for the shell and tube, and when we have a boiling or condensation process, since usually these phenomena occur at constant temperature for the boiling and condensation, especially for the pure fluids. This chart is one of many charts have been prepared by different publications which can be found in heat transfer textbooks such as Allman heat transfer and the one which have been published by Intropera as well, and many other references, and I will put some of them the end of this video in PDF and a link to be found in the description box below this video. The second useful parameter is the fouling factor. And fouling factor referred as R sub F or fouling. In fact, it is a thermal resistance that is presented in the heat exchanger during operation, continuous operation, and it adds another thermal resistance to the thermal resistances for the convection parts in both sides of the tube, shell side and the inner flow, and the conduction part through the tube metal. So this is an extra resistance to be considered because it will accounts for the insulating effect of deposit on heat transfer surface, as we will see that in the design of heat exchangers. For example, This photo shows the deposit of solid material at the inner tube surface, which it is clear that will uh, reduce the heat transfer between the fluid that flows inside the tube and the fluid on the shell side. These resistances usually can be found in uh, tabulated form as shown in this example. We have fouling resistance in units meter square Kelvin per watt. For heavy fuel, it is range between 0.0005 to 0.0009, and for steam it is 0.002. And these values, of course, depend on the fluid and usually the nature of the fluid which is passes through the heat exchanger and the operating conditions such as temperature, for example. This is um, a factor which should be considered in the thermal design of heat exchanger because usually when the heat exchanger is clean, then the resistances are very low and you may find that the performance is uh, uh, very well, and with the time during the operation, these deposited material solids will minimize the heat transfer and deteriorate the efficiency of heat exchanger. Therefore, usually these resistances should be considered in advance during the design of heat exchanger. The fluid flow arrangement in the heat exchanger, and as we are talking about shell and tube heat exchanger, is the same for other types of heat exchangers. So there are two main types of fluid arrangement in the heat exchanger. The first one is called the counterflow pattern, and the second one is called the parallel flow pattern. In the first type, the fluids on the shell side and tube side enter the heat exchanger from opposite ends of the heat exchanger. Therefore, as they are passing through the heat exchanger, the flow is counterflow. And at the same time, when we talk about the other type, the fluids enter from the same end or the tube and shell sides, and they are leaving at the other end at the same direction. Therefore, these fluids, as they are passing through the heat exchanger, they are following a parallel path. So if we talk about the counterflow heat exchanger, if we have a look at the blue line, which represents the cold fluid, it enters at T sub Ci and leaves at T sub C naught. And when we have a look at the exit temperature, it will be there is a possibility to be higher than the exit temperature of the hot fluid. On the contrary, there is no possibility if we have a look on the right hand side um, graph, the cold fluid as it enters at T sub Ci, then it leaves at T sub C naught, which there is no possibility to be higher than the exit temperature. And in general, all the heat exchangers are preferred to have a counterflow. And in the counterflow, there is a uniform temperature distribution, and they provide a good temperature difference between both fluids. So it is more efficient than the parallel flow pattern.
ولغرض فهم هذه العلاقة المهمة التي أكدنا عليها بأن الجريان المتعاكس في المبادل الحراري هو أفضل من ترتيب المواع بشكل جريان متوازي. لدينا مثال هنا: زيت المحركات بمعدل جريان معروف ودرجات حرارة معروفة، المطلوب تبريده من درجة حرارة 90 درجة مئوية إلى 60 درجة مئوية بواسطة تمرير الماء في داخل الأنبوب الداخلي inner pipe بدرجة حرارة 30 وسيسخن إلى 50 درجة مئوية. المطلوب هو أن نقارن بين الحالتين بحساب فرق درجات الحرارة اللوغاريتمي لهذه الحالتين. فلو أخذنا الحالة الأولى والتي تمثل الجريان المتعاكس، اللون الأحمر يمثل الزيت الداخل، واللون الأزرق يمثل جريان واتجاه الماء البارد. لغرض حساب فرق درجات الحرارة اللوغاريتمي أخذنا العلاقة سابقا بأنه نحسب دلتا تي 1 والتي تمثل فرق درجات الحرارة عند النهاية الأولى 90 درجة مئوية مطروحا منها 50 درجة مئوية والناتج 40 درجة مئوية. بنفس الطريقة ممكن أن نحسب فرق درجات الحرارة عند النهاية الثانية وستكون 60 مطروحا منها 30 والناتج 30 درجة مئوية. لو طبقنا القانون العام MTD equal دلتا T1 minus دلتا T2 على أو مقسومة على اللوغاريتم الطبيعي natural logarithm للكميتين دلتا T1 مقسومة على دلتا T2، والناتج سيكون 34.76 درجة مئوية. بنفس الطريقة يمكننا أن نطبق القانون التابع للجريان المتوازي. الزيت باللون الأحمر 90 يبرد إلى درجة حرارة 60، والماء سيسخن من درجة حرارة 30 إلى 50 درجة مئوية. وهنا يمكن أن نعيد تطبيق نفس العلاقة. دلتا تي 1 عند النهاية الأولى سيكون 60 درجة مئوية، ودلتا تي 2 عند النهاية الثانية سيكون 10 درجة مئوية، وبالتالي دلتا أو logarithmic mean temperature difference سيعطي 27.91% درجة مئوية. من هذه النتيجة، من هذه القيم، فإن ذلك سيكون كمحصلة نهائيا أن متوسط فرق درجات الحرارة للجريان المتعاكس سيكون أعلى من فرق درجات الحرارة للجريان المتوازي. وهذا بطبيعة الحال لكون الحمل الحراري ثابت، وأيضا معامل انتقال الحرارة الكلي للمبادل أيضا ثابت ولا يتأثر كثيرا بتغير درجات الحرارة، فسيكون لدينا المساحة السطحية للمبادل عندما يقوم بالاتجاه المتعاكس، واستخدام هذه الميزة ستكون أقل مما عليه في حالة الجريان المتوازي، وبالتالي المساحة السطحية يعني عدد أنابيب إذا كنا نتحدث عن مبادر القشرة وحزمة الأنابيب، أو وأطوالها أيضا. وبنفس الطريقة عندما نتحدث عن الأنبوب المزدوج، فإن ذلك سينعكس على طول الأنبوب المطلوب. وهذا يعني أن الكلفة التشغيلية والتصنيعية وكلفة المواد للمبادل المتعاكس ستكون أقل من الكلفة الإجمالية عندما يكون الجريان متوازي، كما مبين من هذه العلاقة.
And now, my friends, we arrive to the summary. Then we have passed through temperature correction factor, as well the fouling factor, and these factors were considered as important factors in the design of heat exchangers. And then we have comparison of heat exchanger pattern, where we have compared the um, the counter and the parallel flow arrangements, and we have found that the counter flow arrangement is more efficient and more economic. And we passed through practical case studies where can we apply the procedure of calculating and design the heat exchanger. We have also passed through some information related to your overall and how can we calculate it. Of course, there are some important references can be obtained in a link uh, that is seated in the description box. If you found the content of the present episode is useful to you, please share it and subscribe to the channel if you didn't subscribe yet. And I will see you in the near future by another application of heat transfer topic in industry. Bye bye.